So, yeah, well, thank you for coming. So I'm Lomüller. I work at Codeplay for a year now, and I'm currently working on the SYCL compiler and runtime. Ralph Potter is here working on the HSA frontend that he's working on in the context of his PhD, also made at Codeplay and University of Bath. Uwe Donsky is our CTO and is the main guy behind the core technologies that we use and I will present to you today to support C++ on an accelerator using some single source programming models. So just an outline for the presentation. I first started to introduce single programming models that we use. So there's two of them, SYCL and the C++ frontend for HSA. And I will try to show you what kind of challenge it actually brings to the compiler and the way we want to actually handle this. By the time at which, this part, I will present to you the core technology that we're using to support this. I hope you will all understand what kind of challenge we have and how we solve this. And then I will go through a quick performance review just to show that we don't have an overhead, basically, on the generated code that we have, and conclude the presentation. So, single-source programming models. How we program C++, how we put C++ directly inside an accelerator. So, just to make sure that everyone's on the same page about vocabulary, I'll be using the host as being designated my CPU system, where my kernel is, my OS is running. The device will designate any accelerators, GPU, or CPU, DSP, FPGAs, other sort of things. I'll be also using a lot of the work items, which is just a thread in OpenCL. And a work group is a group of threads that can cooperate, so share data, and synchronize. Just make sure that everyone's on the same page. OK, so first programming model that we have is SYCL. So it's an open and relatively free standard from the Khronos Group. It is a pure C++ layers that we use to program directly OpenCL kernels. The idea is really to merge the kernel definitions and all the evocation code and device management inside the same source file and have it presented really nicely. We don't provide any language extensions, so basically when you write a SYCL source file, and if you have the proper headers, you can compile it using any C++ compiler. So the way we compile a SYCL source file at Codeplay is basically using a device compiler to extract all the OpenCL kernels. We compile it down to intermediate representation, so we use peer, and some glue headers. And then we recompile this file using a host compiler and integrate our glue header directly to the host compiler. We compile this down to a binary object. And at the time, you can then execute your kernel like you would do with OpenCL. OK, so this is what the SYCL code looks like. So this is a full OpenCL code. So here you get a bunch of code that will manage your device, manage your data. Just point out that we have this function call that creates an object that we call accessors that allow us to access the data and move the data from device to the host. The host from device. But here, this is what we are interested in, is our SYCL kernel. So I want to extract that and transform this into an OpenCL kernel. What I need is just to copy, well, basically first the lambda body to be executable on the device, and then also get the bracket operator, the ID copy constructor, because we're passing everything for values. And basically all functions that might be called as the operator, the bracket operator, and the ID constructor. OK, that's fairly simple. Now, we still have pointers that are wandering around. And let's say we want to use legacy code that needs to access from row pointers. So I just changed my code. And instead of performing the additions I was performing here before, I'm performing here in this function and just give the row pointers here. That's simple. If I'm compiling from a device, well, I need to get this prototype because nothing's changed. But here's the thing. When I'm executing on an OpenCL device, these data here, PC, PA, and PB, are on a global memory, which means that in order to be the equivalent OpenCL script code, will more match this prototype. And our compiler is actually trying to pass directly all this information, the pointer qualifiers, directly down to the code. There is another little thing with SYCL. It's called hierarchical, and it allows us to play with the thread hierarchy of OpenCL. So remember, you have work items, which are threads, but also work groups, but a bunch of threads that can cooperate. And here, I've got functions called inside a part of a work item, and it follows the normal semantic execution model of OpenCL. Every thread will execute this. But here, I got to call it directly from a part of a work group, which means that its expression here will only be executed by only one thread among all the threads in my work group. That allows us to play a little bit with this. Also, because when we're usually allocating data here, in a sense, I want to share the data when I'm capturing this through the different functors and I'm getting it. And so this will be actually allocated in the OpenCL local memory and not the private one. So again, I do the same trick. Let's say we have the legacy functions that use row pointer or here a reference. The host, each part, so I changed the operation that was performing here to call directly this function. So here, I'm going to do some, and it's always following the right prototype. I don't need to change. But remember, here, for instance, this is allocated in local OpenCL memory. Then, when I'm compiling on device, I want the reference to an int to be referenced to a local int. In here, because I'm losing some accessor, I get to global. So we also want to have different version of the same function here. There is also another little trick. This function is meant to be executed by all work item, and this one is meant to be executed by only one. So it does share the same prototype inference, but it's not exactly the same function. And we want to keep a clear separation between the two. The second programming model that we support is to support the HSAIL. So just a few words about the HSA Foundations. They are defining an intermediate language and a runtime for compute, more or less like OpenCL. It was primarily meant to support heterogeneous SOCs, so basically when you have your CPU and accelerator on the same chip, and more rely on shared virtual memory. And Raf, our PhD student here, made a C++ 14-based programming model to support this. So you heavily rely on virtual shared memory and compile all this code down to HSAIL. So the compilations that is followed is fairly the same. On the device compiler, extract the kernels, compile it down to HSAIL, and the host compiler is taking this, glued the things together, and we have basic same compilation flow. Okay. So this is how this looks like. So this is an actual kernel, and it's passing here row pointers. And because we have shared virtual memory, we don't really care about where the data are. Just let the runtime handle this. Because we're still managing the address spaces, well, roughly, it raises the same challenge that I've shown you before with SYCL. Just one little detail is done one little trick. Here, it will let Clang leave those pointers that are the arguments to basically point normally to the global address space. It will leave this into the address space 0, and all locals will be mapped to address space 1. So there was one huge reason why you want to do this is to be able to easily use structures that normally point to data on the host and import it directly in its kernels. So for instance, if you have a linked list, you can go through all the elements of your linked list directly in a kernel without modifying the Clang behavior when it's compiling a host code. Just to sum up what I'm what I told you is we need a compiler that needs to be able to infer, change the variable and argument types inside all the functions that we are compiling for the device. And need to derive this into many forms. We need to maintain also several device functions separately to support the hierarchical. I'm showing you we made two distinct calls to two different functions. And basically, we use a little bit more information to resolve the different calls. Okay. So how do we implement this? So Uwe is basically the guy who is mainly behind all of this. He's been working on this for almost a decade now. We got a paper that described the technique in IPEAK. It was published in 2010. We had several in-house compilers, C++ compiler. One of the last one was uploaded for PS3, so it was compiling C++ code for the PS3. It was integrated into some games, and we partially found this with the paper project. To have a better support for heterogeneous programming models, we moved this directly into Clang, which allows us to have a better support for everything. We've done also similar work to what I will be presenting to you after, but directly at LLVM been funded partially by the CAP project. But here, everything I will talk about is happening on the Clang frontend directly. So, our offload logic in a nutshell. What do we bring to Clang? Well, some attributes. First one is offload. I will just say, hey, this function is a function meant to be executed on the device. So we clearly identify it like this. We have another one, address space of locals, which just allow us to change local variables address space directly and have it as a nice, with some nice options to keep things flexible. We have a set of hooks to intercept all function calls and variable declarations in order to make things coherent. We have somehow extended overload resolutions to basically support this address space changing thing. Support so what I call multi-space device functions. So basically support the hierarchical things that I've shown you before and taking into account a little bit more of the calling context. And of course, all the offloading core, which basically take a function, host function, and copy it in a new one dedicated for a device. And all the address space inference and promotions shown before. Okay, so here what a code looks like behind the scene for us. So here we get pure C++ functions. So I got a function workload that I will be used both by host and the device. Here we get the host functions that is calling this function. So just let Clang compile it normally. We don't interfere with what it does. It does it well. It does it very well. So we just get this result. It's fine. And now we get to this part. So we get our attribute offload that explicitly say, hey, I'm executing this function on the device. We can put a parameter to say, oh, by default, this is in space 1. And we can just say, oh, this is another space or another kind of device function. Just assign a number to it. There's no relations between the numbers. It's just, you could just replace it by an enum. It's just to assign them in two different spaces. OK. So now, here, I'm calling a function, which I want to actually call this function. But hey, this is in a host. So first of all, I just need to resolve this call. Problem is, this is a global int. It's a pointer to a global int, and this is taking a pointer to an int. So we just changed a little bit how standard conversion are recognized. So this conversion to this one is a standard conversion for us in this specific context. And so we'll get more complex expressions so that this one is fairly equivalent. So it's fine for us. So now we have matched it to this host function. But it's a host function, so we need to duplicate it and say, oh, we'll be executing the new one on the device. So first of all, we need to compute the prototype. So we go through the AST quickly and infer the new return type. we can then build the new function prototype. So if there is conflict in the return type, in the return types, we raise an error because we can't compile this. And once we get this new prototype, well, we use the tree transform to take the host function and copy it, clone it into a new one. For each variable declarations that we have, we infer its new type based on the initializer. So here, I'm creating a local variable, initialized using arg plus 4, so doing some pointer arithmetic. So arg is a pointer to an int. Here, this pointer to global int. So my result here is pointer to global int. And we go on with all the compilations. So at the end, we get the initial calls that is binding to this function. And we derive the new functions to this one and bind it directly. That's fairly how it is. And if inside we're calling new functions, also in the host, well, we apply this recursively to duplicate all the functions that it is required. Just a little bit rules about the overload resolution. So we follow the standard rules. We don't interfere with this. We don't want to interfere with this. But when we are calling using device functions, then we need to add some one or two rules. So when I'm calling a function, for example, call here, I will always try to match it into the same space. So the caller is in space 2. I'm making a call to the function call. And oh, I got a nice match here. So I'm calling this directly. It's fine. Another one is this one. So here, caller is now in the address space 1. Sorry, in space 1. But the function I want to call is, there is two calls here, one in space 2 and one is on the host. There's no match. So what I take is this one, because by default, this is what we take. We always take the host as a baseline, and then derive it into a new one. So here, I'll just match it to call, and redo all the work that I've shown you just before. If this is not possible just to match it directly to the space 2. So sometimes you can have ambiguous calls, such as this one. Here, this is space 1. And when I'm making my call, here, I'm trying to match to those functions. But I only have offloaded functions. The first is in space 2, the second is in space 3. Doesn't match. The call is ambiguous. I can't resolve this call. So just let it like this. Oops. Oh, sorry. We can swap spaces. So let's say this function doesn't exist, for instance. Only the space 2 is existing. Then the call is not ambiguous because I have only one candidate. So I can match it directly. So that's how we switch space. Also, now because we have the offloaded states is part of the signature. So it's totally fine to just change a function, to only change the return type of a function. So here this one is written just a pointer to an int, and a float into a global, and here a pointer to a local. That's fine, because what will make the difference is where we call this function. So, okay, so I presented you the basic lines of everything we do. This will not allow you to directly implement. That is, it is the support for single programming models. We still need to add some language-specific things. So the final compiler and products. For this, for SYCL, we need to define what is a kernel entry point. So we use an attribute, SYCL kernel. I've not shown you this before because it's completely hidden from the user. And so these attributes actually appear in the parallel for that the user call. You don't need to see it. Just only the runtime and the compiler that will need to manage it. Ralph had taken a slightly different path. So you've already seen this attribute. And so we clearly identify where the kernel entry point is. You also have a mechanism similar to SYCL, where you can just provide a lambda and it gets called by a device. All the language restrictions, so HSA is fine with function pointer, but SYCL is not. So we need to add some checks that we don't use any function pointers inside a SYCL kernel. And basically also all the compilation products is specific. So SYCL is we are compiling down to Spear. For the C++ funcset for HSA, we're compiling down to HSAIL. And so that's two different things. Some performance figures. So this is the easiest one. I've taken from the AMD app SDK, option 3, the discrete cosine transform that is performed. I convert it into a SYCL kernel. So using all compilers, I'm compiling the SYCL down to Spear and give it then at runtime to the Spear runtime, to the SYCL runtime for execution. I've taken the OpenCL code, I compile it down to Spear as well, and give this to the OpenCL runtime for evaluations. Well, we roughly have the same performance. So we don't have any overhead from this point of view. That's quite nice. The performance evaluations for the HSA front-end for Math is a bit more tricky. So there is a huge bias here. This is using the HSA infrastructure. This is using the OpenCL infrastructure. OpenCL is much more older than the HSA one. So here it is indeed a bit slower, but well, this is caused mainly due to the bias. Also, some instructions at HSA are not generatable. Some kind of instructions that we can generate in Spear for OpenCL. We can't generate this in HSAIL. And obviously, OpenCL can take advantage of it. And we can also guess that the OpenCL runtime is much more optimized. But when you look at the code, there is no obvious reason why this is much more, a bit more slower. Okay, just a few conclusions. So OpenCL, so all this core technology is a single source enabler technology for us. It offers a great level of flexibility through the call graph duplications that we manage. So deriving all this host function part, device function parts in space 1, in space 2, and whatever. With the excellent overloading resolution logic we have is basically able to handle this properly and maintain all the C++ rules that we want to maintain. And thanks also for the address space inference and promotions, we do this all in the front end. So when we generate final code, well, everything is already there. We don't have to infer new address spaces and stuff. So with the call graph duplications, allow us to have a clear separations between what is host and what is device. And there is no overhead on the generated code. If I might also add as more personal opinion, I'm a guy who's worked mainly on LLVM before, working on code generations. And when I read the Codeplay, I started to work on Clang on this. I did a lot of mistakes, by learning and playing around with Clang. But Clang is still staying stable, even though we are quite stressing it by putting them in positions it's not necessarily meant to be. So thanks to Kubernetes, this Clang is really a great tool to work with. So, thank you. Sorry. Yes, just a little bit. If you want to play a little bit with offload, we don't provide as it is, but you can use a compute CPP with your SYCL implementations. And offload is really the core technology behind. We have an evaluation program if you want to test it. It's not open source. Sorry about that. But if you want to test it, you can register your interest in our website and get back to you with the working implementations. So thank you for your attention. And if you have any questions.
Thank you, Victor. Thank you for this great talk. So we have 15 minutes for the questions. So go ahead. Okay, so I will start with one question then. So how do you think that all the current discussion on the mailing list about how to articulate all this discussion about organization of the offloading architectures, how to bundle the various executable or binaries for the devices may be helpful for you? I think yes.
For what I understood, the path that the community wants to take is more towards compile everything using normal address spaces, and then we infer everything down more to LLVM. I'm guessing for CUDA or other programming models, it's much more interesting to do so. Even though I think it is possible to use this kind of techniques. This is our solution to the problem. It's the one we've taken, and I find it quite interesting and nice to handle this at this level. It also brings a new interesting point is because type is changing, we can also reinstantiate templates and play with types directly in the front end, and LLVMIR is not suited for this.
There's been recent work in Clang to support very similar patterns as this for CUDA. Have you looked at any of that? Is it something that you could reuse? Is there any ability to kind of share code here?
Perhaps. So I think for what I understood, but you're talking about GPU CC, right?
But mostly just the overloading based on kernel stuff and similar things to what you were talking about.
For what I understood is it's more relying on interspace inference later on the compilation stage. So that would be two different strategies. Perhaps we can share a great amount of code. It might be. I'm not completely aware of all the work in the community.
Yeah, I guess this work is older than the
upstreaming
of
like
the
10
GPU
years
CC
now.
effort. So
Yeah. We worked on this for Uwe Dolinsky, so it's our CTO, worked on this for past 10 years.
So I'm a little bit curious about the results comparing HSA and OpenCL on given GPUs. So are you using OpenCL2 capabilities or
it was OpenCL 1, so that's why we actually have copies here. So we're copying data and sorry, no, OpenCL 1.2. So we have copying data and then executing it properly. This is using virtual shared memory. We might also incur some
virtual shared memory on the left side.
Yeah. So this is a Ralph frontend, so it's using shared virtual memory, where this code is not.
Okay. But since in OpenCL2 you have also shared virtual memory,
yeah, but
maybe you could, my question is that, what would be the performance? Mainly 10 or something more on
I think
the
we'll
right?
be more close to this.
Yeah, but on this slide, because if you remove the copy part of OpenCL, would it be faster than HSA or not? So
sorry?
My question is that if you use OpenCL2, would we have something faster than HSA or not, or slower?
So this is Ralph work, so I'm not completely aware of everything it's done for experiments. I'm guessing we'll see quite similar performances. This is also one bias in between comparing those two, is this is two different runtimes as well. So the tools that are behind, which we don't have any control over, are different at some point. So channeling, especially HSA, is quite new. So perhaps all the optimizations that could be there are not there yet. I have no insight on how they handle this in the back end.
Okay, any other questions? Don't be shy. Since we have still plenty of time. No? Okay, let's thank again the speaker then.
Thank you.